Hi guys, I'm Monica. I welcome you all to my channel Aerocur. In this video, we will be looking at fluid flow models. So in our previous video, we spoke about coefficient of drag and its values and other fluid properties as well. Proceeding a step further in our aerodynamic journey, we will be developing the equations, basic equations for aerodynamics. But previous to that, we have a small procedure to be followed, that is how to develop these equations based on what we are going to develop these basic equations for aerodynamics. So that is what we are going to discuss in this video. So without any further delay, let's get started. Now let us observe what is this procedure that we need to follow in order to develop the basic equations of aerodynamics. Now we have one physical procedure involved that we need to perform in order to build the basic aerodynamic equations. We have three steps in it. What is the first step? Invoke three fundamental physical principles. What are those three fundamental physical principles? The first one is mass conservation. The second one is Newton's second law, and the third one being energy conservation. Now, what is mass conservation? Mass conservation is something which says mass can neither be created nor be destroyed. And Newton's second law, all of us are pretty much aware of it. F is equal to ma, that is force is equal to mass into acceleration. And energy conservation states that energy is neither created nor destroyed. It changes only from one form to another form. So these are the basic fundamental three principles that we need to invoke in our equations when we are building them. The second task that we do is determine a suitable model of the fluid. Now, how are we going to determine this suitable model of the fluid is what we are going to discuss in this video. And the last task is to apply these physical principles to the model of the fluid. Now, as said, we are going to look at the second step, that is determine a suitable model of the fluid. Now, question arises, what is a suitable model of the fluid? Because fluid is a squishy substance and therefore like a solid, you cannot have prescribed boundaries like a solid. For example, you have a cylinder, you have certain prescribed boundaries. You have a rectangular box, you have certain prescribed boundaries. But in case of fluids, you do not have some prescribed boundaries when it comes to fluids. It is a very squishy substance. Now, how are we going to visualize this squishy substance and apply these three physical principles? That is the task. So in order to do that, in order to study this squishy substance, we have three different models developed. Those three different models are finite control volume, infinitesimal fluid element, and the molecular approach. Let us first look at the finite control volume approach. In this finite control volume approach, let us first consider the streamlines. We have general streamlines which are flowing in the fluid, that is the flow of streamlines. And in between these streamlines, I consider an arbitrary space. This arbitrary space, I call this arbitrary space as control volume, which is in short known as CV. We call control volume as CV, and this control volume is denoted by the letter V. It is denoted by the letter V. And this black enclosure, what we have considered over here, we call it as our control surface. This is the first approach. Now, on the right hand side, you can see that my control volume over here is blank and the fluid is not crossing through it. These streamlines are not crossing through it. So what are these two approaches? What is the difference between these two? In one, the fluid is crossing through it, and in the second approach the fluid is not crossing through it. So what is this change all about? Let us have a look. Now, as I said, we have imagined an closed volume which is drawn within a finite region, and this is the control volume. Now, there are two possibilities. What are those two possibilities? The first possibility is that this control volume is fixed in space and the fluid is moving through it, which is this figure. That is, let us say this is our figure A, and where my control volume is fixed over here and the fluid is moving through it. But we also have a second possibility, right? What is that second possibility? That my control volume is itself moving with the fluid. My control volume is not stationary. So this is my moving control volume. So what happens now? Why are we not seeing anything going through this control volume when it is moving with the streamlines or moving with the fluid? The reason being, as the fluid is moving, the control volume is also moving. So which means wherever the fluid element moves, my control volume is also moving. So this control volume is considerably a large finite region of flow that we are considering in order to analyze our flow. Now what we are going to do when we will build the equations is that we will apply the physical principles to this particular control volume, that is the fluid which is flowing inside this control volume and through this and crossing this control surface. In case it's moving with space, we will be applying crossing the control surface. Now, what exactly we are doing by considering this control volume is that instead of considering the whole flow field, we are just considering a small region of flow. In this particular region, I want to analyze my flow. What do I mean by analyzing my flow? I want to obtain the flow behavior in this particular region. Flow behavior here means obtain the particular flow properties. Moving on to our next method, that is infinitesimal fluid element approach. Now, unlike the previous method, here you can see that there is a small cube that I have considered. The streamlines being the same, moving with the fluid. This small cube shown over here, we call it as an infinitesimal fluid element. So we are imagining that there is an infinitesimally small fluid element within a flow, within our flow, and it has a differential volume of dV. So this fluid element is something as same what you consider in our differential values that you consider in your differential calculus, but it is large enough that it contains huge number of atoms and molecules. So therefore this fluid element can be viewed as a continuous medium. Now again we have two possibilities, that is the first one is my fluid element is fixed in the space, that is the space which I have considered where the streamlines are flowing, my fluid element is fixed. What is my second possibility? That the fluid element is moving along the streamline. Now, when this fluid element dV with a volume, differential volume dV is moving along with the streamline, it will have a velocity v. As we discussed earlier that velocity to a streamline is always tangential, as you can see here. The same procedure we will follow. We will apply the physical principles to this fluid element over here. This was our second approach. The last approach is the molecular model. Now, in case of molecular model, what you do is, now in reality, what is the motion of a fluid? It is a ramification of mean motion of its atoms and molecules. So in this, what happens is, You consider the microscopic approach, that is, the physical principles are directly applied to the atoms and molecules, and this usually comes under kinetic theory. Now, what are the real life examples of this control volume fixed in space? I've considered a particular region. So, as aerospace engineers, we have an aircraft over here. Let us say this is my air flowing over an aircraft. Okay. And let us consider this aircraft is in cruise condition. If I want to analyze flow over an aircraft, then which type of approach this will be? My aircraft is also moving and air is also moving, that is my flow field is also moving, and aircraft is also moving, so which means this is my moving approach, and we will be analyzing the movement of the fluid on the surface or across the surface of the aircraft. Now my question is, give me an example of where the control volume is fixed and the fluid is flowing through it. So there are many simple real life examples that you can come up with. This question I leave it to you. Thank you for listening. Stay tuned.